Welcome back to the epic conclusion of this three-part mini-series. So in the last two videos, we prepared a Raspberry Pi with Void Linux and a web app that we wanted to host. Now in today's video, we're going to set up our very own VPN so that only we can access our Pi, even through public networks. And by we, I mean me. Please don't steal my Pi. Before we set up our VPN, I figured it might be good to explain how VPNs actually work and a little about networking. I want you to understand our VPN's configuration so that you can adapt it to your needs. We've all been on YouTube at least once in our lifetimes, so I'm sure we've all heard about commercial VPNs like Nord and Express that promise unlimited security and privacy if you just buy their service. You ever wonder how they work? In a nutshell, a VPN just encrypts all networking traffic between 2 points. If you're connected to a VPN and you try to access some website, your request gets encrypted on your laptop, sent over the network to the VPN server, decrypted, and then sent on to the server for the website you requested. The website responds, and that response goes through the exact same steps but in reverse. This gives you two things. Number one, your initial request gets encrypted on your device before ever touching the network. This means whatever network you're on, whether it's an untrusted public network or your local ISP, it cannot read your request. The only thing it can see is that you're sending unknown data out to a VPN server. Number two, it gives you anonymity. Somewhat, but not really. Your request still gets sent the same as it did before, but it's sent from the VPN server along with requests from 1,000 other users. The idea is that your ISP would no longer know what you're accessing, but in reality, unless you're taking additional steps to mask your fingerprint, your request that leaves the VPN server could still have enough data on it to fingerprint who you are. And yes, even your VPN provider has an ISP that can monitor their traffic. So that's all beans, but how does it apply to our self-hosting situation? The VPN service that we're going to be hosting is going to be exposed to the public network, and it gives us a doorway into devices that are on our private network, but only devices that have been pre-configured with the proper encryption keys. Any other device that tries to connect is going to be turned away by the VPN. I'm also setting up my VPN so it doesn't have access to other devices on my network, only the device that's running the VPN, which is my Pi. Additionally, we only want our requests that target our Pi to transition through this VPN. All other requests should ignore our VPN and get sent out like normal. This is called split tunneling. To make all this secure, our VPN needs to know how to reliably identify my laptop and not be fooled by someone trying to impersonate me. It does this through asymmetric keys. I'm by no means a cryptography expert, but the gist of it is we generate a pair of keys for the server and a pair of keys for each device that we want to connect to the server. Each device holds on to its own private key and never shares this with anyone. Their public keys, though, are exchanged with whoever they want to connect to. This key exchange happens during setup time, not during connection time. When they do attempt to connect, they complete a challenge which involves signing something using their private key. The other end of the connection can verify their signature using the public key that was exchanged earlier. And thanks to the magic of math and cryptography, this is all done in a way that takes a few milliseconds to verify, but the lifetime of the universe if you wanted to try to brute force it. The last thing I wanted to talk about before we dive in is CIDR and subnet notation. An IP address is made up of 4 groups of numbers that each range from 0 to 255. If you're doing the math, that's 256 numbers each, or 2 to the power of 8, which is a fancy way of saying an IP is 4 groups of 8 bits separated by dots. Each group is sometimes referred to as an octet because it's 8 bits. How do you specify a range of IP addresses, though? If I want to specify the range 10.0.0.0 through 10.0.0.255, how would I do that? Most of the time, you'd use what's called CIDR notation, CIDR, which looks something like this. The number after the slash indicates how many bits in our IP address should be locked. 0.0.0.0/0 is a common way to say any IP is valid. The /0 at the end indicates 0 bits should be locked. meaning all 32 bits that make up our IP can be whatever they want. The other extreme ends in a /32. If we have 192.168.1.1/32, that says all 32 bits should be locked, meaning the only valid IP address in this so-called range is 192.168.1.1. If we use /24, such as 10.0.1.0/24, that means the leftmost 24 bits should be locked, but the final 8 bits can be whatever they want. That gives us the range 10.0.1.0 through 10.0.1.255. Okay, enough technical nonsense. Let's get into setting up our VPN. We'll be hosting a WireGuard VPN server to access this breezy agenda app I threw together. To get situated, over here on the left I have 2 terminal sessions that are SSH'd into my Pi as my main user, Ben. On the right side, I have a terminal session that's just on my MacBook. No SSH for this one. The first thing to do is install WireGuard on the Pi. You can do that with xbps install, and then let it do its thing. After that, we'll generate 2 pairs of keys, 1 pair for the server and 1 pair for my MacBook. If you have more devices that you want to connect, you'll want to generate a key pair for each device. I'm going to put all my keys inside this WireGuard keys directory that I just made in order to keep them in one place and make it easier to clean them up later on. To generate a key, you'll use WireGuard's WG utility. In this one command here, I generate both a private and public key for the Pi server. And I'll use the same command but with different file names to generate a key pair for my MacBook client as well. Alright, now to create our WireGuard config. We're going to create and edit the etc WireGuard wg0.conf file. Feel free to use whatever text editor you prefer, but just make sure to edit it as sudo. First we configure our interface, which is a fancy way of saying the server. We need to tell it what its own private key is, so for that I'm going to print out the pi server.priv, copy the output, and paste it in. Next is the address. This defines a subnet which WireGuard devices are a part of, while also specifying which IP the Pi server should use. A subnet is basically an IP address range that's used for a particular purpose. In our case, our virtual private network. My router already assigns my devices with IPs starting with a 10.0.0, so to avoid conflicting with those, I'm going to use the 10.0.1 IP prefix. To lock those first 3 numbers while allowing the 4th number in the IP address to differ, we're going to use a /24, which we described as the CIDR notation from earlier. That means our VPN is comprised of IPs ranging from 10.0.1.0 to 10.0.1.255. We're also explicitly telling WireGuard here that the Pi server interface should be given 10.0.1.1 in this subnet. The listen port is the port that we're going to be exposing to the outside world. This has nothing to do with the port of the web app we're going to be hosting. This is the VPN's port. By default, WireGuard uses 51820, so I'm just going to stick with that. Next, we list out all the peers that can connect to this WireGuard VPN. We need to provide the public key for each particular peer, which is inside of our MacBook client.pub file. Then we configure the range of IP addresses that this peer is allowed to have. This range should be within the 10.0.1.0/24 subnet that we defined earlier. I'm going to explicitly assign it to 10.0.1.2/32, which locks all bits in that IP address. It says, this client will have this exact IP address and nothing else. When we set up the client, we're going to need to tell it that it should use the IP 10.0.1.2. If you happen to have multiple devices that you want to access your home server remotely, then you're going to add a new peer configuration for each one. Just make sure you increment the allowed IPs for each, and set each one's public key appropriately. The server configuration is done now, so to enable the WireGuard service, we just need to create a symbolic link from the provided service config inside of etc/sv to /var/service, and it should start up. To confirm it's listening properly, you can run wg show wg0 to show the 0th WireGuard interface that we just set up. If it prints an error, then something is wrong with the configuration. One issue I ran into earlier was that I didn't have the .conf suffix on my wg0 config file. So if it's not working, also double check that the config file is actually named properly. Now onto the client config, which I'm going to be doing over in my MacBook terminal session. I'm currently just in an empty directory that I'm going to use to store my config file, but you can really put this file anywhere you want. I'm going to call it piserver.conf, since it's for connecting to my Pi server. I know, real creative name. This also starts by configuring an interface, but since this configuration file is for the client, the interface section represents the client. It gets a private key as well, which is the MacBook client private key file that we generated earlier. The address that we give it should match exactly what we configured for it on the server side. In this case, it's 10.0.1.2/32, since we wanted to only use this exact IP. Now for the peer section. This represents the server we're trying to connect to. We'll give it a public key, which is the Pi server's public key. The endpoint of the VPN is the external IP address given to us by our ISP. An easy way to find it is to go to whatismyip.com, copy the IPv4 value it gives you, and then tack on the correct port, which in the server's config, we'd specified as 51820. The allowed IPs is a range of IP addresses that should be sent to this VPN. Any request that goes to a different IP should leave our MacBook just like it normally would. Only these IPs should go into our VPN. There's just a single IP we care about, and that's the internal IP address of our Pi server. That IP address is 10.0.0.120. The IP you'll put here is almost guaranteed to be different than that. In usual fashion, I'm going to be putting a /32 on this, since I only want requests for this exact IP to get sent to my VPN. And lastly, the persistent keep alive value just ensures that our VPN stays active. Not really too much to say here. Now I need to install the WireGuard client application for my MacBook. This is what I'm going to use to turn on and off my VPN connection. So to do that, I'm just going to head over to their website, click on Installation, grab the macOS download, which annoyingly sends me to Apple's App Store. Once I download and open it, I'm greeted with this interface to manage my WireGuard tunnels. In our terminal, we created this piserver.conf WireGuard config file. That's the one we want to import here. So I'm going to go ahead and do that and allow WireGuard to add a VPN configuration to my Mac. There's one more piece to the puzzle, and that's to make our VPN accessible to the outside world. For that, you're going to need to set up a port forward in your router, which basically says, hey, if a request comes into my network looking for a specific port, send that request to a particular device. Every router is going to be a bit different, so I can't give you the exact steps that you're going to need, but I can show you how I do it with my router. I just use the router that my ISP gives me, and they annoyingly force me to do all my configuration through their wonderful app. So in their app, I'd go to my Wi-Fi settings, then advanced settings, find something that says port forwarding, add a port forward, choose the target device I want to use, which in my case is my Raspberry Pi since that's what I want to direct requests to, set the port number to the one that we configured for our VPN, which was 51820. The TCP UDP option I don't think really matters too much, as long as you choose an option that at least has UDP. I'm going with just UDP since I don't believe WireGuard uses TCP at all. Then I say next, and I'm done. Now to see it all in action. First, you can see here that my Agenda app is indeed running. I'm still connected to my local network, so there's no need to use my VPN to access it. If I switch over to my phone's hotspot, wait for it to connect, and then refresh my browser page, suddenly it starts spinning indefinitely. The page never actually loads. If I go up to my WireGuard icon in my toolbar and activate my Pi server config, or I can do it over from the app window, suddenly the page loads. It's not the fastest because my phone signal isn't the best where I am, but it does still load. Since it's all confirmed working, I'll go ahead and shut off the VPN and switch back to my home network now for some cleanup. So we don't actually need the certificate files anymore that we had generated earlier in the video. To make sure they don't fall into the wrong hands, I'm just going to go ahead and delete them. Poof, all gone. Made it to the end, Mr. Frodo. You followed along and set up your own server. I think you should give yourself a pat on the back. You did a pretty cool thing. As I mentioned in the first video, this mini-series was just to hold you over while I get some research and planning done on the main Breezy devlogs. But in the next video, we should be back to our usual content. So hope you enjoyed the side quest, and I'll catch you in the next one.